can't believe we're finishing week 7. It's crazy.
Yes.
So, today we're kind of continuing our chemical tour of the hydrologic cycle. We'll talk mostly about lakes, a little bit about rivers as well. But the thing I want to highlight are sort of dissolved oxygen and the relationship between oxygen and nutrient supply. Nutrient supply is what kind of controls the base of the food web, how much photosynthesis happens. How much photosynthesis happens, therefore reflects how much kind of fuel there is in an environment for respiring organisms to subsequently decompose it. Photosynthesis creates oxygen, respiration destroys oxygen. In stratified bodies of water, we develop a situation when it gets extreme, it's called eutrophism, which is where there's so much respiration that the oxygen gets driven down to quite low levels. And so we'll talk about those interrelationships today. As I say, there's like a gradient of activity between having lakes with no biological activity, where the dissolved oxygen is primarily governed by things like solubility, as we've talked about before, and lakes that have a lot of biological activity. And you can find other environments, estuaries, rivers, bogs, etc., where these same conditions exist. But like I said, I choose to use lakes because that is pretty simple dynamics. So the first thing to talk about is dissolved oxygen. Schematic of a lake that has very little biological activity. So that the dissolved oxygen is primarily a function of Henry's law, right? And I'm just noticing a little bit. There should be a divided by sign in there. So fixing that. And Henry's law, which is the solubility thing that says that actually there shouldn't be. I apologize. Shouldn't have fixed that. I have it written in a slightly rearranged way, which is instead of saying concentration, you can plot this with the pressure on the other side and say that a constant is basically the concentration divided by the partial pressure, or vice versa. The key thing is that this is temperature dependent. For a lot of gases, when it's cold, we can put more gas in water, and when it's warm, we can put less gas in water. And when there's no biological activity kind of affecting the oxygen, then the oxygen concentration in the lake is largely a function of temperature. And we've talked about that before, and I'll remind you of that in a moment. But the main process is sort of exchange across its boundary, right? Gas going back and forth, and how efficiently can it do it? And this, color gradient is meant to say something about temperature, kind of going from warm to cool as it goes down. There is a pressure dependence as well, right? So it's not just temperature, but the pressure effect is significantly smaller. Okay, and the key thing is that in a lake like this, it's pretty much oxidized throughout, right? So the water, has sufficient oxygen for us not to be going down the redox leg. Now this is a lake where we've entered in photosynthesis. So photosynthesis also makes oxygen, right? And it happens in the upper part of the water column. Depending on the size and shape of the lake, photosynthesis may happen throughout, but it is depth limited because it requires light. And in cases where the lake is not specifically highly stratified, then and where photosynthesis and respiration is balanced, right? We make some oxygen, we exchange some oxygen, just like we do in the other lake. We have some respiration, but we stay in an oxidized environment. Part of this process would be the liberation of by respiration of nitrate, right? Look back to the photosynthesis and respiration, the Redfield equation I gave you. One of the ways we can express respiration, the breaking down of organic matter, is to make some carbon dioxide, some water, some hydrogen ions, some phosphorus, and some nitrogen gets liberated. And so that can be released from the water by nitrification. And if this process, if there isn't too much kind of external forcing on nutrients, if it's kind of slowly building up in the lake over time, then the nitrogen concentration, which is one of the two key nutrients along with phosphorus, it's kind of under control, which continues to be oxidized in the bottom waters. So this is that photosynthesis respiration equation I was mentioning, right, where photosynthesis goes in this direction and respiration goes from here back. This is the nitrate that's liberated that denitrification speaks of. But so now imagine a scenario where you've got this reaction happening a lot, right? And you're consuming a lot of oxygen, so you're going in the respiration direction. You're putting all the stuff in the water, and for whatever reason, we're not getting a lot of photosynthesis down there. That's going to reincorporate and go in the back direction. It could be just light limited, could be because of particle content or something like that. In that case, this process will keep going on, or animals will keep digesting algal protoplasm as long as it's there. And it can take the oxygen down to really low concentrations. And this is a process that when it happens in lakes, we call eutrophication. Furthermore, there's something called cultural eutrophication, when human activities increase the rate at which this happens in surface water, and we load this stuff into the environment. That stuff falls down to the lower part of the water column, and we get this kind of reaction happening on steroids a lot. And so we consume more oxygen in the bottom waters because we're loading the surface water with nitrogen and phosphorus. And you're probably too young to remember this, but in the 70s and 80s, there was, especially in the 70s, there was pretty much every soap that you bought, every laundry detergent, dishwashing soap was loaded up with phosphorus because it's really good for taking grease off the stuff. You can still go to the store and buy TSP, like if you're going to paint your walls or something, which is just trisodium phosphorus. But everyone was using phosphorus in their laundry detergents and their dishwashing and so forth. It was loading the environment with phosphorus. We're having this problem of eutrophication all over the world, not just in North America and in Europe, but it was certainly acute there. And so there's been efforts to kind of scale way back on the amount of phosphorus or even the presence of phosphorus in a lot of those cases. And that's part of the story of eutrophication, is the recognition that, especially for phosphorus, which is kind of solubility limited in water, putting in a lot of extra phosphorus, especially phosphorus is pretty soluble in water, is going to upset this balance and ultimately cause more of this consumption of oxygen, the back reaction, the respiration, because somewhere else we fertilized it and produced a bunch of algal protoplasm. So before we get there, we have to talk a little bit about dissolved oxygen, right? And which is oftentimes written as DOX, but it's dissolved oxygen. It's usually given in percent relative to saturation. And the saturation changes with temperature. So this is something called a nomogram that people use to kind of figure out, well, how much oxygen should there be in the water as a function of temperature? So the temperature scale up here. This is a concentration of oxygen. And you can draw, and then this is the percent saturation. So you can say, okay, for exactly saturation at 100%, let's say at 20 degrees C, you draw a line from 20 through the 100, right, like this, and see where it intersects down here. And they'll tell you, oh, okay, the value is something around 8. The one value that you can kind of take to the bank is the 25 degrees C value. Line comes through here, it's 8.6. It's just like, I don't know, something that I was forced to memorize at some point in time. And that's what that looks like. That's just a line, okay? And this is for typical average barometric pressure, right? If you were in a lake on like the top of Mount Everest or something, it would be a little bit different. But so now let's look at the lines for a colder condition, right? And see what happens to the solubility. So this is right at freezing, okay? Now we draw a line through 100, you see, whoa, it's up there like 14.5. Right? So as temperature varies, as temperature gets colder, solubility goes up, okay? So there's more oxygen. So you might say, well, a colder lake or lake in a colder environment should be more resilient to this eutrophication process I was just alluding to previously, which would be true. And the warmer the climate, the more sensitive it is, right? If we get up to really warm temperatures, the scale doesn't even go as far as 40 degrees C, but if it did, we see that that lake would have something closer to 5 or 6. So it's less. Okay, so now there's some terminology that we like to use that relates to oxygen. Some of these you may have heard of before in different contexts, like these same terms are used for health status, for instance. So hypoxia, when we're talking about it in the environment, is a specific condition where oxygen goes below 2 milligrams per liter. And the key thing about this definition is it's an absolute concentration, right? So depending on where we are on the temperature scale over here, right, 2 is down here. You could draw a 2 and go through and connect it to whatever temperature we have in the environment. Let's say it's 25 degrees CO2 up to 25, and you'd see that, well, at 2, we're something like 20% of saturation, right? Whereas if we were at a colder temperature and we drew our tie line through, we'd see a slightly different result. Okay, and the reason that value is set, okay, 2, not just an arbitrary number, is that for most organisms that respire, that are complex and not counting single-celled organisms that live in bottom waters, in lakes, and as well as in the ocean and the coastal zone and everything else, they need 4 milligrams per liter or higher for like normal metabolic function. So 2 is like half that. I mean, you know what it's like to be in an environment with low oxygen. It's hard, it's stressful on the organism. And 2 is a concentration below which functionally we start to see really negative ecosystem impacts. Doesn't mean that there are awesome negative impacts of 2.5 or 3 or whatever, but for some reason 2 is a kind of a significant number. It's half of 4. 4 is really this threshold for normal health. So that's kind of why it's defined. And you'll read in the newspaper about hypoxic areas, especially in the coastal ocean. Those are areas defined by having, less than 2, regardless of the temperature. So if it's warm or cold, doesn't matter. This is set by anoxia is the complete lack of oxygen, 0. And we all know that, we have, because of the log scale and everything else, we can have 0.1, we can have 0.001, whatever value of milligrams per liter. It never goes to true 0. But as soon as it drops into the decimal places, below 0.5, we call it anoxia. And of course, this is worse. This is harder on the environment. And environments may migrate back and forth between hypoxic conditions and anoxic conditions, depending on local supply conditions. They may even go back into oxidized conditions and sometimes called oxic or oxia. And it just depends on the setting. It depends on what's causing the anoxia or the hypoxia in the first place. Okay. Now, there's 2 other definitions that we use all the time. I've used one term, eutrophic, RE, today. This is different. This is based on a relative percent of saturation at a given temperature, right? So it's a slightly different, it's an older terminology that we use in the environment that people have migrated to this, but this one has more leverage because, as we'll see in a moment, there's additional terms. There's a mesotrophic as well. But basically, this is defined as the concentration of oxygen being below 10% of the saturation value at a given temperature. So whereas this is an absolute thing, this one depends on the temperature, right? Like if you go back over here to this diagram, you say, well, what is 10% of 8.6 is 0.86. 10% of 14.46 is 1.46. So at the boundary of the definition of eutrophic, the concentration is going to be different, right? Whereas 2 milligrams per liter is always 2 milligrams per liter. So this is why people have kind of migrated away from this eutrophic, oligotrophic terminology. Oligotrophic means there's at least 25% of the saturation value at a given temperature. Okay. And if you think about that, at 25% of 8.6, right, which is a 25 degrees C saturation value, is something like whatever it is, 2.15 or so. So it kind of matches up with this. These things, they're at 25 degrees C. Okay, so if we want to think about the budgets of nutrients in an aquatic system, we have to think about all the places they can come from. And I kind of go through these arguments, and we've talked about them before, but I just kind of want to remind you that there's very little nitrogen in the atmosphere that isn't N2, right? Just nitrogen gas, which organisms don't really use. There's a little bit of natural production of NOx, this group of nitrogen oxides that we talked about last time, NO, N2O, NO2, and N2O5. That happens in like lightning strikes and in huge forest fires, but it's really, really small. So there's very little natural nitrogen that comes from the atmosphere to the land surface what we call fix, something that biological systems can use, okay? And there's obviously anthropogenic sources, right? We put a lot of nitrogen in the atmosphere, as we talked about, and that enhances that amount with negative effects. But still, in terms of, relative to the amount of nutrients that are available in many aquatic ecosystems, even the nitrogen that we're loading in the atmosphere that's causing acidic rain is not changing the amount of nitrate that much in the water column. It does change it a little bit, but it's a pretty minor source. The other main nutrient, which is phosphorus, this is, mostly insoluble. It's in particulate, inorganic forms, mineral grains, sorbed onto iron particulate surfaces, etc. We don't really find this stuff in the atmosphere. So even though for a lot of composition and a lot of parts of the hydrologic cycle, we kind of look to the atmosphere as the starting point and say, okay, well, what comes from there? What's added to it by other processes? For the nutrients, we don't really have to worry about the atmosphere. It's just not that big of a deal. There's a little bit of it. I have a few slides here that kind of summarize, like, well, how much nitrogen and phosphorus is there in rain over the oceans and over the continents? And the reality is it's super low here and it's low here. A little bit higher in terrestrial rain, especially over agricultural regions where we're kind of like bumping up the system and putting particulates in the atmosphere. It's low in both cases, but it's effectively zero over the oceans, and it's like very tiny numbers over the continents. And there's some maps here that kind of show you this, how it looks over the 48 states of the continental US in 1955 and in 1980. It has increased, and the place where it's highest has changed. So it used to be kind of, this is for nitrogen, higher in the west. This was largely driven by internal combustion. Stuff coming out of cars before there were catalytic converters, completely unregulated. People out there cruising in their monster gas guzzler cars. And emissions controls, sort of led by California, have reduced that so that by the 80s, that's gone. Now, there's a big spike up here in the Great Lakes region, not nearly as intense as this spike, but that's from a combination of kind of agricultural and industrial practices. Still small on the grand scheme of things. Now, this is ammonium. This is another source of nitrogen to the atmosphere. This is primarily driven by agricultural processes. And so you can see the map looks a little bit different between, there's a slightly different time frame of it. This one is 1955 again, not seeing the label of it. And this one is 1980. The one additional complication is that, and this is in your reading, in case you want to kind of follow up with it, but these two maps use different units. So you have to make a conversion to be able to compare the concentrations, which I put down here. So that's a slight complication. This is in micromoles. That's in milligrams. But in any event, actually this one's in milligrams, this one's in micromoles. So this one here, I converted the value for you. It exists, especially in the center of the country, again, agriculturally driven, but it's not a major thing. Like, we don't find lakes and rivers in this part of the country suffering more in general from this excess nitrogen addition from the atmosphere than other parts of the country. It's not the kind of leading cause of issues. So once we get into the water is in the hydrologic cycle at the surface of the earth, where we have rivers and we have lakes. We look at, well, where does the nitrogen and phosphorus there come from? So it's primarily discharged from soil. Okay, so we've got ecosystem processes, things happening up on the land surface, things happening in the soil column that are basically producing organic matter through photosynthesis and breaking it back down through respiration or other processes that can happen in the soil, for instance, driven by fungi. And that puts a certain amount of nitrogen in the water, right? And the relative proportion of these things depends a lot on the particular ecosystem, climate factors, soil particulate content, et cetera, et cetera. As a little aside, if you recall, last time we were talking about acid deposition on the landscape, one of the things that acid rain does is protonate the clay sites, negatively charged clay sites that would normally be binding ammonium. So that when we do that, we release a little bit of extra ammonium from soils which makes them a little bit less fertile, but also it means that this stuff gets into groundwater or surface water, it can discharge into lakes. So it's kind of like a double whammy there. It's not the key problem from acid rain, but it does contribute to the addition of ammonium, which is a nutrient, into aquatic ecosystems. So that's happening. Now, for phosphorus, is a little bit more straightforward in the sense that pretty much all the phosphorus, naturally speaking, without sort of any human induction, is coming in as particulate matter, right? And so if you recall, I've used these terms a few times, but if we talk about dissolved inorganic phosphorus, it's DIP. That tends to be pretty low. It's solubility limited. It's sometimes called orthophosphorus. It's various forms of phosphoric acid and its conjugate bases. So it's present, but it's pretty small compared to what we call PIP, which is particulate inorganic phosphorus, and POP, which is particulate organic phosphorus, which is basically residue of organic matter that's still got its phosphatic units in place. Okay, so because of this, because the phosphorus is generally insoluble, because there's nitrogen present, usually in excess, but not a super huge excess when sort of naturally driven, most ecosystems have kind of conditioned themselves unperturbed by human activities to sort of just use up the right amount of nitrogen and phosphorus, but usually phosphorus is limiting in the aquatic ecosystem because its solubility limited. It's usually like a little bit extra nitrogen, which means that while you can throw a bunch of nitrogen or a bunch of phosphorus into a lake and enhance the photosynthesis, it's easier to do with phosphorus because it's always like wanting a little bit more, okay? So a lot of the nitrogen and phosphorus that we find in the hydrologic cycle is in a form that can't be readily utilized by organisms, but with a small amount of transformation, meaning digestion by respiring organisms, can be converted into that form. So it's kind of like money in a long-term account in the bank that you can't take out right away. But so anything that increases either the standing crop of reactive nitrogen and phosphorus or the stuff that's being transported as particulates in the ecosystem that then can liberate nitrogen and phosphorus in utilizable forms can affect the rate of photosynthesis. The way I want you to think about the rate of photosynthesis is basically how much oxygen do we produce is one of its things it does, and how much food do we produce for respiring organisms downstream. Okay, so today in our modern world across the globe, we as humans have changed the nitrogen and phosphorus cycles by roughly a factor of 2. Some people argue more. You can find some places where it's cranked up by like a factor of 10. So like a lot of other stuff we've talked about in this class, it's difficult to go and say, oh, here's a pristine environment that has no impact by humans and here's how it works. We kind of know how it works, but we also kind of know that even in the best cases, systems are being perturbed by human activity, some more, some less, but there's a significant impact. And that affects everything from how biologically productive a lake is or a river, as well as how much oxygen is there. So I've got a few slides coming up. I'm just going to summarize what's on those slides first. They look at the relative proportions of nitrogen and phosphorus in kind of rivers in North America. For nitrogen, for instance, well, how much of it's dissolved and how much of it's particulate, right? It's like close to 1-to-1. It's not exactly 1-to-1. It's a little bit more in the organic matter particles, but it's roughly 1-to-1. Whereas for phosphorus, it's 1-to-10, like most of the phosphorus, 90% of it is particulate. Then when we look at the relative proportion, this is just all, whether it's inorganic or organic. This is like, well, how much for nitrogen in a dissolved form is inorganic, ammonium, nitrate, nitrite, versus organic, like amino acids and all kinds of things. And you can see here that something like 2 to 5 or 40%, however you want to think about it, is inorganic, and 60% is organic. Organic is the stuff that can be broken down by respiring organisms to make inorganic forms. We call that process remineralization. So you can see what that proportion is like. And for phosphorus, it's a slightly greater proportion is in the organic form, okay? And And so organic form, relatively soluble, easy to distribute in the environment. And human activities have significantly enhanced some of these things, but none more so than this. This is the laundry detergent and that kind of stuff. So these are these tables. They're easier probably to just kind of look through on your own, but again, they're in the reading. And this kind of shows you, well, what does a nitrogen cycle look like? Kind of what's the total that we deduce? How much, you know, for an individual environment is, you know, how do these break down as percentages of the total? And how much of this in pink is anthropogenic, meaning like humans affected it. So you can see here, well, like, yeah, the amount of nitrogen that's going into biological fixation, which means photosynthesis and the building of algal protoplasm, is 139 teragrams of nitrogen per year. And of that, the estimate is about 44, you know, or whatever that is, like a third or so of it is anthropogenic. You can look at the fertilizer and industry. Well, 100% of that is anthropogenic. You can look at how much is coming out of, you know, precipitation in various environments. And you can see that more than half of that is anthropogenic. So that stuff is coming onto the land surface. That's what's called inputs. You can also say, well, what's coming off the land surface, like as runoff? And you can look at these various things, you know, denitrification, which is the biological process of converting nitrate back into nitrogen, for instance. You can also have direct degassing out of soils. You can have kind of river flux concentrations. You see sort of a similar story. But interestingly enough, you'll see that humans have had more impact on the inputs to the land than on the outputs, which gives you some idea that maybe some nitrogen is building up and being stored in this kind of very gross generalized model. So now here's a little bit more detail about the forms that that nitrogen is in. This just tells you about the relative proportions of inorganic and organic and particulate for nitrogen, as summarized 2 slides ago. Now for phosphorus, and this stuff on the last 2 slides for nitrogen, the equivalent content for phosphorus is all compressed into 1 slide here. So it looks at, you know, orthophosphorus, that's the DIP, the dissolved organic phosphorus, the DOP, the particulate organic phosphorus, POP, particulate inorganic phosphorus, PIP, right? And the relative proportions. And again, you can see here, human activities, something like a factor of 2, right? So we've doubled those cycles. So you can imagine if you start to think about, well, you know, these numbers are sort of abstract or whatever, but just like on average, if we add twice as much nutrients into aquatic ecosystems, we should expect twice as much photosynthesis in surface water. As long as the lakes are mixing and churning, that's okay. But as soon as the lakes stratify, we're basically doubling the flux of organic matter from the surface down to depth, where photosynthesis doesn't happen. We're doubling the food source, right? It's kind of like America's obesity epidemic. You add more food, organisms are going to eat more food. When they eat more food, they consume more oxygen. They drive the oxygen content down. And that's the basis of this idea of eutrophication. It's actually a natural process, but humans are cranking up the rate. So that's how these cycles work. And so you can actually look in environments. So this is a map of, or a diagram, I guess I should say, of a bunch of different rivers, and different watershed regions, right? And it shows you, well, how much nitrogen is being deposited on the landscape, right, through all the various things on that last set of tables, and how much is coming out if we measure it in streams, right? And this is a 1-to-1 line. That would be like, okay, all the nitrogen we put on, it comes back out, the world's in balance. Places up here are places where there's nitrogen, more nitrogen coming off the environment than going into it. There are a few, they're all agricultural, and that's not the common condition. The common condition is to find lakes, especially or rivers, in environments where there's more nitrogen deposited on the landscape that's coming back. What happens is that ecosystems tend to develop abilities to hold the nitrogen, because nitrogen is very labile, it's very reactive. And so the way the holding happens is by storing the nitrogen in these inorganic forms, these organic forms. right? So you can see a lot more nitrogen in organic. That stuff can't just like kind of degas back to the landscape. It needs to be remineralized by organisms. And so it's like I say, it's kind of like money in the bank. Ecosystems can use this nitrogen when they need it. It takes a step. Something has to decompose from organic matter, liberate some nitrogen, but then it's there. Okay, and so that's why this is, something that is called ecosystem holding. However, you can find conditions where an ecosystem becomes saturated, meaning it can't keep up, it can't hold back its nitrogen. That's what condition these guys are in. It's usually places that have been super over fertilized, and there's really high rates of respiration happening in soil columns, and so it's spitting the nitrogen back out. It's not as typical. So another thing, so that leads to this idea that, okay, in agricultural environments, where like there's a lot of nitrogen applied to the fields and so forth, we tend to find nitrogen fluxing through those settings in a way that's very, very impacted by human activities, much more so than phosphorus. Because the soils are particulate based, the kind of general thinking is that more often than not, terrestrial dry ecosystems, so not aquatic ones, but dry ones, tend to be limited by nitrogen. There's always enough phosphorus. And so it's more common to find soil amendments that include nitrogen and phosphorus and potassium and phosphorus. Doesn't mean you don't add some phosphorus, but this stuff here is more susceptible. When we get into the aquatic part, it flips because of the solubility thing. So that phosphorus, as being so insoluble, becomes limited. So when we go into urban environments instead of agricultural ones, where we find a lot of utilization of phosphorus in various kinds of processes that happen in cities, degreasing agents in your auto body shop, as an example. There are still soaps and detergents that are used that way as well. We tend to find more phosphorus than nitrogen in the waters running off of urban environments. Right? You can find examples that are different than that, but this is just sort of like a general notion. So if we compare the nitrogen to phosphorus ratio in an environment, we compare it to the Redfield ratio, right? Remember, the Redfield ratio is the thing that we get from this generic equation of photosynthesis and respiration I showed you right at the beginning, right? Redfield ratio says that in photosynthesis, we're going to consume nitrogen and phosphorus in a ratio of about 16 to 1. Okay, and when we decompose organic matter, we're going to liberate it again in that approximate ratio. So if we go into an environment with a lot of extra phosphorus being added in, we expect to find in the water something different than 16 to 1. You'll have more of this and less of this. In a place where there's like a lot of extra nitrogen, we'll have more of this than this. But in a system that's completely balanced, where photosynthesis and respiration are the primary control, we find roughly concentrations varying in a ratio of 16. So, this is a map. I'm using a plot again. It's got phosphorus across the bottom, got nitrogen across the top, micromolar concentrations. These are both log scales, right? This line in green is the 16 to 1 line. That's the line that says, yeah, photosynthesis and respiration is the main control in this environment. And you might say, oh, well, that sounds natural, right? And it's true if you're down in these concentrations. These are the typical anticipated natural concentrations. If human activities enhance the amount of nitrogen and phosphorus in such a way as to promote more photosynthesis, more respiration, and to crank up these concentrations, but we stay on this line, we're going to have a perturbed environment, but the concentrations are still controlled largely by biological activity. But if we go into an environment that's down on this side, kind of below this, right? This is the nitrogen to phosphorus ratio equals 1. This is a place where extra phosphorus has been added into the environment. Extra phosphorus accumulates in those environments and drives extra photosynthesis. Up here are the settings where we've got extra nitrogen. Extra nitrogen in and of itself in an aquatic ecosystem isn't as problematic because there's all these different mechanisms for microorganisms to employ to remineralize that nitrogen and have it come out of the water. I'm not saying it's not a problem at all, because it can be, but much less of an issue than extra phosphorus. So we find, both conditions, depending on where we are, but kind of more industrialized and more biologically driven. But so there's really the only kind of pristine settings is ones down here with low concentrations of both, close to 16. Okay, so now let's think a little bit about lakes. We've already talked about how lakes stratify, right, during most of the year. This is what a concentration profile with depth looks like for 3 parameters: oxygen, phosphate, and nitrogen. This is a plot from a German book, so they're spelled a little bit differently. You can see each one of these chemicals has its own concentration scale. But the thing you see is something called a classic nutrient profile during periods of stratification. What a nutrient profile looks like is low in the upper water, high in the bottom. And the reason this is happening is because up here we got photosynthesis happening in excess of respiration. So any of the free floating nutrient in the water is absorbed by organisms, algal protoplasm, and pulled out of the water. Okay, now those organisms, they live, they thrive, they die, they fall as particulates to the lower part of the water. Down here, there's no photosynthesis, so it's limited because the light is limited. But there's animals that remineralize or liberate or digest that organic matter. So the concentrations come back up in the water. At the same time, you can see oxygen up here, which right at the surface is controlled by exchange with the atmosphere. So even if we get extra oxygen from photosynthesis, this is going to diffuse back out. We rarely find above saturation values. But when we go down with depth, below the thermocline and into the deeper layers in the hypolimnion, then we see low oxygen concentration. And so these two things mimic each other. In fact, they should mimic each other by exactly the amount that we predict by the Redfield ratio. Right, that's why I'm not going to go back into that equation, but there was a diagram that showed you plus minus the relative molar proportions of the oxygen, nitrogen, phosphorus ratios. Some ratios you can pull off that diagram are, for instance, the relative change of nitrogen to phosphorus across this profile that's driven by photosynthesis and respiration should be 16 to 1. There should be a slope. Like if we went and collected waters throughout this lake at a bunch of different depths, we would find the relative rate of change of nitrogen to be 16 times as much as phosphorus. If photosynthesis is recovering, is driving it. And for oxygen, we find, and that would be a positive slope because they're both on the same side of the reaction equation. Oxygen is produced when nitrogen and phosphorus go down with photosynthesis. Oxygen is consumed by respiration where nitrogen and phosphorus go up. So we get a negative slope in this case, with a ratio of about 9. Right, and that comes from 138 moles of oxygen to 16 moles of nitrogen, which is just part of that Redfield equation. So now you can think about lakes as kind of being a cycle, right? Because remember, they don't always stratify. Sometimes they mix, they do various things. But if we think about them in the most kind of simple box model-y way, which means that we're trying to do a budget, the lake is a reservoir, and we're looking at fluxes in and out and transformations that happen within the lake. There's a certain amount of photosynthesis and respiration, which is controlling the carbon dioxide and oxygen balance, as well as the nutrient balance that shows up here in this profile. And it tells you photosynthesis mostly being done by, algae in the water, and the respiration mostly being done by single cellular organisms that are kind of controlling that. So, the fish and the heart organisms are not the primary control on the oxygen profile of the nutrients. They play a role, but they're not the main thing. It's microorganisms, and why that's important is that they tend to respond very quickly to changes. So in lakes that stratify, we see these, we call them nutrient profiles. We see these same exact profiles in the oceans because the oceans stratify, and we'll talk about them in a second. They stratify over different periods of time, and the development of these patterns happen over different time scales. But the shape of this thing called a nutrient profile, low in the surface water, high in the bottom water, is a common thing that you'll hear people talk about. Now, rivers are a little bit more complicated, right? Like the river flowing into this lake or out of this lake, because they're churning and mixing so much, we tend not to see stratification values like that. We may see sort of integrated compositions along a river, right, that might reflect the input of, more photosynthetic material or less. But because they are churning, they are constantly resaturating with oxygen. Okay, there are examples, we go through them in the environmental class where, especially when rivers are flowing kind of slowly, humans can put in so much stuff that it can make the rivers go anoxic. You find this especially in estuaries where water tends to get stuck there because of tidal forces and so forth. So the Thames River in London is a good example. It's actually an estuary, and it used to go completely anoxic around the turn of the 19th century and smell really bad. You think about the old days where they're like throwing their poop in buckets out into the street. Yeah, so this has been happening for like a millennium there in a very unfortunate environment. But what we tend to see in rivers is if there's a really high loading factor of phosphorus or nitrogen, then yeah, we can see some imbalances, but they're a little bit less straightforward than anything. So I've shown you this plot a bunch of times before, but I just want to remind you, because now these terms should mean something. Oligotrophic and eutrophic. In a oligotrophic lake, where the biological processes are relatively limited, the oxygen concentration is primarily driven by temperature. So during the turnover events in the spring and in the fall, there's mixing throughout the water column to get constant temperature profile, constant oxygen. During the stratification periods where the water on top is less dense than the water below, we get the development of these profiles. So the one in the summer, the temperature is warmer on the top and cooler on the bottom. There's nothing happening to cool the bottom water. It's just that the bottom water has got the same temperature profiles it had previously, but the surface water is being heated up by the sun. So that concentration, as the temperature goes up, the concentration of oxygen goes down, just in a purely inorganic Henry's law sense. In the winter time, where the stratification is driven by that kind of density peak of water at 4 and the very, very cold water at sort of anywhere between 0 degrees C and 4 floats, then we get the opposite effect. The water's even colder, so the oxygen saturation is a little bit higher. Okay, so that's what it looks like when there's no biological activity. Now you add in biological activity of the kind, shown here, and during stratification, these nutrient profiles develop. The more extreme the oxygen depletion is, this curve can go down, it can go all the way to 0, as it does in that other example. It's a function of how much extra respiration there is relative to photosynthesis. How much respiration is largely a function of how much food is there. So in this example, and this is just an example, oxygen is driven all the way to 0. That means that we have that condition of anoxia, right? A hypoxia condition would have this oxygen come down, but still stay at 2 milligrams per liter. So we would have some finite value here. It would come down, but not, this is 0 or 4, so it would end up somewhere like about here. That would still be bad. Hypoxia equals bad. This is anoxia, which equals worse. And you can see how it develops. And it's not theoretical, even though this only takes a few months to go from here to here to here to here. We see these profiles develop in lake after lake after lake. And this causes this condition of eutrophication. And as I kind of mentioned before, eutrophication is a natural phenomenon, but human activities greatly enhance the rate at which it develops over time. So these are some samples of water taken from Lake Zurich in Switzerland. That's kind of why the text, a lot of stuff is German. These all come from a single book called Sturm and Morgan, which when I learned aquatic chemistry, that was considered the Bible. It's kind of been, hasn't been updated in many years. But these are concentrations of oxygen versus nitrogen, oxygen versus phosphorus dissolved, and of nitrogen versus phosphorus. And each one of these yellow lines are the lines predicted by the Redfield ratio. Right, so here's your 16:1 line. Here's your 138 over 16, which is a line with a 1:9. And your oxygen to phosphorus is going to be 138 over 1, just in terms of molar quantities. Okay, and so you can see here that, the lakes don't fall in a line perfectly, but pretty darn close, right? These are samples taken all throughout the water column, kind of representing different spots along a depth gradient and then also areally, and then plotting up their concentrations. We can also see what's called the overturn values. this is the part of, or turnover values, I guess. This is the part where the phosphorus is the lowest and the oxygen is highest. That's like, what do we have up in the surface water right before the lake turns over and mixes? Because then that'll be the stuff that the lake gets homogenized at when it goes to this, condition here, and here, which are notably the same, right, in these two examples. They're different during stratification, but during turnover, they're roughly the same. Okay, so now when we go to the ocean, it's a little more complicated. I've shown you this diagram before. This is the kind of flow chart of the currents, the deep currents in blue and the shallow currents in red. And in the ocean, what we find, if we make a kind of a similar plot, this has got three things on it. It's got phosphorus, it's got carbon, it's inorganic carbon, it's got nitrogen across the top, right? What we find is that if we look at waters along this gradient, right? So the surface waters are pretty similar throughout, just like they are in lakes, because of various processes that help allow stuff to flux back to the atmosphere. So as we go along this gradient of flow, which can take over 1,000 years, during the current configuration of how the oceans overturn and the salinity and pressure and temperature variations and the kind of limitations of how the continents drive the flow pattern. As this water moves along, it gains the signature of extra respiration. Because there's always photosynthesis happening above it, there's particles falling down into it. Over time, we get more and more nitrogen and phosphorus building up in the water and less oxygen, right? We also happen to build up some carbon dioxide from respiration. So even though the oceans are entirely basic, they become a little bit less basic along this flow path. And so we can plot up waters in deep waters, right, in the oceans. And what we find is that in the Atlantic to Indian to Pacific, in the deep water, we see the concentrations of phosphorus and nitrogen go up because of these infalling particles. And so we have stratification, we get nutrient profiles, but whereas for a lake, these things can develop, in just a few months, and we can get overturning a couple times a year. In the oceans, this is like a millennial process. It's happening, but it's a millennial scale process. Okay, so now this is just another reminder of the surface flow patterns that are shown with a little bit more detail. These green places are places where water that is flowing along the deep ocean comes back up. Okay, it's called an upwelling zone. And so we have kind of upwelling in a lot of places of the ocean, but in upwelling zones, we tend to have really focused flow of deep water that have very high concentrations of nutrients and low concentrations of oxygen, supports a lot of photosynthesis. That's why the California current is so ecologically diverse and rich, because these upwelling zones tend to happen on the eastern sides of oceans, which are the western sides of continents. This has a lot to do with how the Earth circulates, the extra driving force of the water masses as they move along the current by something called the Coriolis effect, which tends to pull water offshore. So this is kind of a flow chart showing you the surface water conditions and the deep water conditions. The deep water being formed up there in the North Atlantic, re-enhanced in the South Atlantic, flowing along, receiving particle flux from above, which is adding in nutrients and so forth, and promoting the decomposition of oxygen. And then the return flow in red coming along the top. And these places where there's upwelling provide nutrients back up into the photic zone. But so if we just look at the profiles of nutrient concentration with depth, right? So you can see here, these go full ocean depth, 0 to 4 kilometers. And we look at the three, places in the simplified model, middle of the Atlantic Ocean, middle of the Indian Ocean, middle of the Pacific Ocean, you'll see that nitrogen and phosphorus increase as we go down, right? The surface water is about the same, but nitrogen ends up in the deep water a lot less than it is in the Indian and the Pacific Ocean because of this infalling particles. Same thing for phosphorus. Interestingly enough, most of the action happens in the Atlantic Ocean. The Indian and Pacific are not all that different. Where we do start to see differences is if I give you a plot here of carbon dioxide, you see that Pacific Ocean really is significantly less basic than the Indian. So this is another plot of nitrogen and phosphorus, just like that Lake Zurich data, but this is now for the oceans. Okay, and this basically shows you, and I put the 16:1 line on there. And again, the waters pretty much follow that. The one places where the oceans kind of fall off of this is in the coastal zone. Because you've got a lot of particulate coming in off the continent, and that can throw things off. But once you get out into the open ocean, this is what it looks like. And the deepest, oldest water, the stuff that surrounds us here in Hawaii, that upwells in the North Pacific, has the highest concentrations of both, because it's the oldest water on the planet. Seawater, I should say. Okay, so lakes fit the Redfield paradigm a little bit less good than the oceans, in part because of the more complications in the terrestrial or terrestrial organic matter composition. But to a first order, the principles are the same. So I don't want you to kind of worry too much about the differences between oceans and lakes. So we've talked a little bit about nutrient limitation already. I just kind of want to remind you what that is. It's kind of a stoichiometric thing. It's like saying, okay, we look at what's required for photosynthesis and respiration, and we can write out a fuller version than the Redfield equation that includes all the micronutrients as well if we wanted to. And whatever concentration of whatever chemical in the environment is the lowest, we call the limiting nutrient. Turns out for aquatic terrestrial ecosystems, phosphorus is almost always the limiting nutrient. Sometimes you can find places where iron is a limiting nutrient, because iron is another low solubility thing, especially in the open ocean. This can be the case, that if only there were a little bit more iron coming in on particulates in dust, we would have a little bit more photosynthesis. This is one of the things that helps make the oceans more productive during ice ages, because there's more winds and more particles. Yeah.
There's actually I forget what group of science researchers did it, but they got iron dust, iron oxide, like dust, and then went out to the ocean and put it in the water, and they literally created a huge algal bloom.
Yeah. And there's a few people that were kind of pushing this idea as a way to help mitigate climate change. In my opinion, the problem is that anytime you take a natural ecosystem and you perturb it, you have unanticipated effects, right? And it is true, you can fertilize the ocean, especially the Southern Ocean, by putting in iron and making more algal protoplasm. But what are you doing to the rest of the food web? What are you doing to the bottom waters? What are you doing to the sediment? It's like it's a debate that we have, right? And so I think it's true that people have done that. For most freshwater parts of the hydrologic cycle, the water component, at least, phosphorus ends up being the limiting nutrient. And this is why human impact of loading phosphorus is so important. And so this is just, I've shown you a similar table before, but this is a table showing you the nitrogen phosphorus demands by plants. And you can see here that the phosphorus demand ratio, demand over supply, is higher. That's what makes it limited, right? Plants need more in a relative sense than they're getting in an unperturbed environment. So if we add extra phosphorus, we can add extra respiration, because that's the thing that's holding back, extra photosynthesis. That thing's holding it back. Trying to see where iron is on the scale. Here's iron, right? And so for most, it's low, right? This is like a factor of whatever it is, 80 as much. The oceans are a little bit different, especially the Southern Ocean, where once you get away from the coast, most of the insoluble stuff that we find is supplied by wind, like little particles that are blowing in dust and so forth. So this gives us the idea that adding extra of the limiting nutrient can overload the environment, overstimulate it. So this is an example of an area in upstate New York where there's a series of lakes that are kind of experimental lakes. They've been doing stuff to them for several decades. And this is two lakes right next door to each other where pretty much everything about them before humans started affecting them was the same. Same inputs that come in from river water, rainwater, and soil water, groundwater discharge. This one here, they've been adding a little bit extra phosphorus. This one they haven't. And you see how different the water looks. Clear and blue, primarily driven, there's some photosynthesis and respiration in there, but not enough to cloud up the water. And it's driven by the natural cycle. You put in extra phosphorus to make the extra algal biomass. Okay, this upper water is like very oxygenated, but as soon as this stuff dies, it's going to sink down in the lake and it's going to get respired and not be so great. You can also see that because you have so much particulate content in the water from the algal biomass, it limits the amount of light that can get down below the surface layer. So you have less photosynthesis in a net sense as you go deeper down into it.
What happened with Lake Erie back in the 50s
Yes,
and
I'll show you a
60s?
little bit of Erie data. I mean, Erie's complicated because it's a big, long lake, but it's especially on the sort of Ohio side of it, really shallow. And so it gets into a really super stratified condition. So yeah, the Great Lakes, which are huge and much harder to upset the balance of, because just the quantity, the standing crop of phosphorus is so high already, has definitely seen this kind of impact. So I have a couple graphics here that kind of illustrate eutrophication, which is basically what this phenomenon is. Where basically various things are coming off the land surface in a natural sense. We've got leaching of nitrogen and phosphorus out of terrestrial ecosystems, building up the water, supporting more photosynthesis, supporting more respiration down here, and building in the development of these nutrient profiles. And that can be added to by activities that happen on the land surface, whether they're agricultural or industrial. There's one interesting thing, part of the reason why I added this, because you don't usually see it here, is that it says here thermal pollution, right? So if you heat up the water, like in a power plant or what have you, you're also reducing its ability to hold oxygen. Even if it's just 1 degree, just think back to that nomogram I showed you, that's going to be a couple milligrams per liter of oxygen that can hold its saturation. So here's another example of a lake where a curtain was put across it and, no phosphorus addition, yes, phosphorus addition. There's some shallow water on, adjacent to a golf course. And again, this is what eutrophication looks like in detail. You can see these filamentous algae. And, you can probably imagine what this lake smells like during parts of the year. I don't know how controversial it is or not, but for instance, golf courses are one of the very, very worst things for loading neighboring aquatic environments with nitrogen and phosphorus. You put a ton of that junk on there to make the grass look all good. And if you had to pick one thing to target that are effectively useless, I mean, agriculture is a problem, but at least it's providing food, right? I mean, what do golf courses give us, other than Donald Trump? So I know there are people that really love golf as a game or whatever, but they should be able to play on brown grass, right?
Mhm.
So this gives us the idea of life cycles of lakes. Okay, a typical lake, just think about like however water gets dammed up. You could have like a glacial situation with a moraine and water builds up there. You could have landslide event that cuts across a river. Whatever happens to create a lake, initially that lake is going to be in an oligotrophic condition, right? Where there's very little biological activity happening there. The oxygen is controlled primarily by inorganic things. And over time, a little bit of respiration happens, a little bit of photosynthesis happens. We start to develop this during stratification, the buildup of nutrients in the bottom water. And every time the lake overturns, that bottom water that's a little bit richer in nitrogen and phosphorus is put back up into the photic zone. And every year it makes like a little bit more photosynthesis and respiration in the surface water. So it starts to build up and hold phosphorus and nitrogen relative to the rate at which water flows through the lake. And if this happens long enough, then the lake is going to naturally go eutrophic. Okay. And that gives us this kind of lifetime idea. And, after a certain point, the biological activity will get so intense that the lake will fill in with organic rich sediment and it'll become a meadow or a bog or something else. Okay. So the question is, how long does that take naturally and how have humans portray it? So in this system, an oligotrophic lake is a young lake, a eutrophic lake is an old age lake, and there's something in between that we call mesotrophic, which has some moderate value of oxygen below saturation. Not as much impact on biological activity as eutrophic, but still, along the path. So, we can ask ourselves about like, well, how long does this take and everything else. And one of the things I like to think about is something called the relative residence time. We talked about residence times before, which is just the flux in or out of a reservoir and the reservoir size, right? So if you take the reservoir size and divide it by the flux, you calculate residence time. And a relative residence time is just the rates of two things compared to each other. So here I'm going to show you the relative residence time of a chemical relative to water. Right, so we got water flowing into a lake, we got water flowing out of a lake. We can calculate a residence time. We also have some chemical I, could be any chemical. We're going to use it for phosphorus, but it could be any chemical. And it's in the water, it's flowing into the lake, it's in the lake, then it's in the water flowing out of the lake. You can imagine a scenario where if we calculate the residence time of I, the chemical I, and water, and if their ratio is 1, then that chemical is the same as the water, right? It's coming in with the water, it's leaving with the water, staying the same time as the water. We find lots of examples where the relative residence time of a chemical is higher than the water. It means it's got to be building up in the lake. Phosphorus is in this category, right? When we look at the inflow and outflow of a lake and the concentration and we calculate the residence time, in most cases we come up with a value that's higher than the residence time of the water. Now, you can also have chemicals where the residence time of that chemical is less than the residence time of water. These tend to be, they're things that move faster than water in the environment. It's the chemicals that, for instance, are gases that might be able to degas out the surface and not make it into the outflowing water. And I basically just written out the equation for the residence time of I in the orange boxes, right? Residence time of chemical I is just concentration of I in the lake divided by its flux, right? We do the same thing for the water. The residence time of water in the blue box is basically the water in the lake divided by its flux, okay? But now I'm going to do some fancy math to that, which is transform things into the green box and the red box, right? So I'm going to take this equation and think about it as this, instead of being residence time of residence time, this part is the concentration. It's the grams of I in a lake over the grams of water, which is just a concentration. And this one here is the flux of I with time over the flux of water with time. The with time goes away and just becomes the flux of I relative to the water, which is basically the concentration of chemical I relative, either coming in or out, right? Because this is an amount, a quantity over an amount of water. So basically, the relative residence time, this is approximate, obviously, but you can measure this relative residence time by just looking in a relative sense at the concentration of a chemical in the lake and the concentration in the stream inflow, right? And so if the lake has more of a chemical than the stream flow feeding it, that chemical is building up, right? And this is the case for phosphorus, okay? Oh, sorry, I have that in there twice. That's why. The life cycle of lakes is such that in the natural case, you can go allotropic to eutrophic to fill in a century to maybe as much as 10,000 years. And where that 10,000 year example comes from is the Great Lakes. They were formed at the end of the last ice age, about 10,000 years ago. And, as you mentioned, Lake Erie has been close to eutrophic, but they haven't filled in yet. They're really big lakes, right? Smaller lakes are going to be faster. And really small lakes can, only last for maybe a century. Maybe most lakes on average are something like a millennium. What determines it is stuff like how big is the lake, how often does it overturn, and what does the watershed look like, right? What's in the watershed? How much nutrients are coming in every year, okay? And that's a natural process. And this is kind of how eutrophication looks like naturally. As I say, in this plot, they say the time is centuries, right? It could be millennia, or in the case of the Great Lakes, it might be, tens of millennia. Cultural eutrophication is the process we use to the enhancement of the inflow of nutrients by human activities that causes this process to happen more quickly. And the question is, well, how much more quickly? And in some cases, by like a factor of 10, so that it goes from centuries down to a decade. Right, we can do it quickly if given the opportunity. So there's some interesting chemistry that's related to this. So one of them is that once we get stratified and the oxygen concentration goes down and the amount of oxygen concentration decrease in the bottom waters is driven by how much nutrient-rich photosynthetic algal protoplasm is falling down from above, being decomposed, right? If the water goes hypoxic and then into eutrophic and even into anoxia, then it becomes so low in oxygen that the iron 3 plus gets reduced to iron 2 plus. Okay, that remember the redox ladder? So it turns out that some amount of the phosphorus in a typical lake is oligotrophic or mesotrophic, meaning on the way to eutrophic. The iron is still iron 3, and the phosphorus binds to that and it goes down into the sediment. There's several different minerals. One of them is a mineral called vivianite. So this iron builds up, this phosphorus builds up in the sediment. And so another factor that controls the life cycle of lakes is, well, how much iron do we have? If we got a lot, we can sequester some of our phosphorus and keep the bottom water from going too high. And just think about the concentration of phosphorus in the bottom water. That's the water that's going to get reintroduced into the surface water every time there's an overturn. So the higher the phosphorus, the more photosynthesis in the next cycle, the greater the food supply and the greater the diminishment of oxygen within. So as long as the waters aren't too low in oxygen, we sequester some iron. But as soon as the lake goes eutrophic, then we start to transform our iron 3 into iron 2. And not only can we liberate the phosphorus bound to iron particles in the water, but it can start to come back out of the sediments. And then the next time we have an overturn, the thing really is on, enhanced rate of photosynthesis. So once we get to this condition, it's kind of a runaway. And this just kind of reminds you of the way in which iron and other redox sensitive chemicals percolate up out of sediments, as we talked about. So this is kind of a graphic just showing you some of the various kind of human activities and how they affect this cycle, right? And so I'm not going to read through it, but they're all sort of like, sewage, city processes, things that happen at feedlots and various agricultural phenomena. They all contribute to the addition of phosphorus. So the last thing I just want to mention is you can actually calculate using the Redfield ratio and some really simple assumptions. Well, approximately how long will it take for a lake to go eutrophic if we start cranking in a bunch of extra phosphorus? Or the way that a lot of watershed managers might use is like, so how much phosphorus can we add to not screw up this lake, right? And so one of the kind of interesting things that you can think about is up in the epilimnion where we got the photosynthesis going on, every time you add a milligram of phosphorus, you make 100 milligrams of algae and 140 milligrams of oxygen. It's just that Redfield ratio mass balance converted into milligram quantities. And then you can take this algal protoplasm, let it sink down into the lake, and if it gets completely decomposed, it's going to use up that amount of oxygen. It's going to re-liberate this amount of oxygen. Right? It's just like, it's a simple calculation. So this is a box model of that exact calculation, where we're making the algae here, the particles are falling down, we're remineralizing them. They've added in some knobs to basically say, well, okay, let's take a little bit of this phosphorus and allow it to stick to iron-rich particles and then go into the sediments. That's what this flux is. And we're going to have some little currents in the lake that return some amount of phosphorus back up to the surface. Like I said, you can change these values to try and match observations to the lake. This is a very simple-minded model. But with this model, you can calculate the phosphorus loading factor. The other thing to think about is that during this process of algae sinking down to the surface, this oxidative process, it takes time, right? It takes time for respiration. So the deeper the lake and or the longer the period of stratification, the more efficient this green arrow can be. And so that results in this equation, which just says, well, the change of oxygen is going to have that same stoichiometry plus some estimation of the time at which the particles are on that transit route, meaning the length of time of stagnation of the lake, time in between overturn events, the loading of phosphorus is coming in by human activities, the depth of the hypolimnion, right? And this is just a conversion unit for days to years. So you come up with these diagrams And this is just the same stuff again. This is the mean depth of the lake and a loading factor of phosphorus. And a sort of a zone, which basically says, okay, we can keep a lake from, this is the permissible load of phosphorus. So you get to a really deep lake, you can put some phosphorus in it. In a really shallow lake, right, this is 1 to 10 meters, you can't really put any extra phosphorus in it. This is just a slightly different way of looking at it in terms of flow rates or flux rates. So this is basically kind of the inverse of the depth, but it also has a residence time of water term. It's the same thing. It's just that the places that are, good or bad flip where they are. But so, I mean, in my opinion, there's no acceptable extra amount, but everything's a trade-off in reality. And so this gives you some idea of how much you can have. How much can you have in your untreated sewage that's being discharged in the environment? Whether that phosphorus is coming from organic matter, I think human waste, or from laundry detergent or any other source. At some point, it doesn't really matter. It's still just phosphorus that gets in. So I think that was, I have a couple examples I forgot about Lake Erie. So this is basically a flow chart showing you time from 1800 and 1800, something like 1975. This is from that same old textbook in German, showing you the Great Lakes and the balance of phosphorus from different sources, detergents, the upstream lake, falling out of the atmosphere, human waste, and land run, right? And so what you see is that as you go along this flow chart, Michigan flowing into Erie, flowing into Ontario, all of them have a spike that's developing, right? So this was at the peak of the eutrophication problem in the 70s. These have subsequently come down, which I've tried to illustrate with those yellow things. But what you see is that, for instance, this upstream lake, this sort of crisscrossy pattern, it's not here, the original upstream lake, it's here, it's starting to get bigger here and here. And you can also see the relative proportion of some of these other things. Collectively, this is what's causing eutrophication in these watersheds. And these are really big lakes. You find it in smaller lakes too, but to affect to such a large degree the amount of phosphorus that we find in these large bodies of water is really impressive. So I just have a couple of pictures of that. So this is basically satellite image, visible wavelengths showing you, for instance, Lake Michigan. And this is a sort of algal bloom associated with stuff running off the shoreline and producing extra nutrient flux. You can see what we have here in Lake Huron. In Lake Erie, this whole sort of western half of the lake is showing this pretty significantly. I think I have one other picture of it. Yeah, this is just something from the news, that talking about what strategies might be employed to kind of not have this happen, for this lake to look, like that.
See my parents' house from here.
Really?
Right underneath the Canadian finger, there's a small peninsula.
Here? This
No,
one?
no, to the east.
Oh, over here.
Down underneath that, there's a small little blip on the north shore of Pennsylvania. That's Erie, PA.
Oh, down.
That bingo.
Yeah. Oh, interesting. Well, so yeah, I mean, this is there's a lot of jurisdictions, right? And there's a lot of finger pointing, especially this idea, well, it's the upstream lake, right? It's not us, it's the upstream lake. So, but it requires an integrated strategy. And I mean, I hope this illustrates that these are complicated problems, right? They are not simple things, but the way in which we impact environments is so significant in so many different ways that it's just, I don't know, it's amazing to me. All right, so I'm going to end it there.